Welcome to General Chemistry 2 class. This section is on acid-base equilibria and salt equilibria. This lesson is about the Henderson Hasselbalch equation. Let's begin. In this lesson, we will calculate the pH of a buffer solution using the Henderson Hasselbalch equation. A buffer is a solution that resists drastic or a sudden change in the pH upon addition of a small amount of a strong acid or a strong base. It consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. Consider the addition for the ionization of a weak acid Ha in water. The acid ionization constant equation for the ionization of Ha is given by Ka equals hydrogen ion concentration times A negative concentration divided by Ha concentration. Taking the negative logarithm of both sides of the equation gives us negative logarithm of Ka equals negative logarithm of H positive concentration times A negative concentration divided by Ha concentration. Applying the product rule of logarithms, which states that the logarithm of xy equals logarithm of x plus logarithm of y, gives us negative logarithm of Ka equals negative logarithm of H positive concentration minus logarithm of A negative concentration divided by Ha concentration. Leaving the negative logarithm of hydrogen ion concentration on one side of the equation gives us negative logarithm of H positive concentration equals negative logarithm of Ka plus logarithm of the quantity A negative concentration divided by Ha concentration. Changing negative logarithm of H positive concentration to pH and the negative logarithm of Ka to pKa, we get the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is given by pH of the buffer equals pKa, or the negative logarithm of the Ka of the acidic component plus logarithm of the ratio of the concentration of the basic component to the concentration of the acidic component. Example 1. Calculate the pH of a buffer solution prepared by mixing 20 ml of 1.0 molar ammonia and 80 ml of 0.80 molar ammonium nitrate. The pKa of ammonium is 9.25. The buffer consists of ammonia as the basic component and ammonium ion as the acidic component. Calculate the final concentration of ammonia and ammonium ion upon mixing. Note that the total volume of the buffer is 100 milliliters. The final concentration of each component is equal to the initial concentration times initial volume divided by the total volume. Thus, we have 0.20 molar for ammonia and 0.64 molar for the ammonium ion. Use the Henderson-Hasselbalch equation to solve for pH. Substituting the value of the pKa and the concentration of ammonia and ammonium, we obtain pH equals 8.74. A buffer consists of 0.84 molar sodium dihydrogen phosphate and 0.35 molar sodium hydrogen phosphate. What is the pH of the buffer? The Ka of dihydrogen phosphate ion is 6.2 times 10 raised to negative 8. Solution. The basic component is hydrogen phosphate ion. Since 1 mole of hydrogen phosphate ion is produced from 1 mole of sodium hydrogen phosphate, the concentration of hydrogen phosphate is the same as that of sodium hydrogen phosphate, which is 0.35 molar. The acidic component dihydrogen phosphate, in which 1 mole of this ion is released from every 1 mole of sodium dihydrogen phosphate. Thus, the concentration of dihydrogen phosphate ion is equals that of sodium dihydrogen phosphate, which is 0.84 molar. The pH can be calculated using the Henderson Hasselbalch equation. To convert Ka to pKa, we need to take the negative logarithm of the Ka, adding the pKa to the logarithm of the quantity, hydrogen phosphate ion concentration, divided by dihydrogen phosphate ion concentration, gives us pH equals 6.83. Buffer capacity is the amount in moles of strong acid or strong base needed to change the pH of a buffer by 1 unit. It describes the extent by which a buffer can resist drastic changes in pH. Consider buffers A and B. Buffer A is made up of 1 molar ammonium ion and 1 molar ammonia. On the other hand, buffer B contains 0.01 molar ammonium ion and 0.01 molar ammonia. The two buffers has the same pH since they have the same base to acid molar ratio. However, buffer A has greater buffer capacity than buffer B since it has greater concentration of ammonia or ammonium ion that can consume the, the added acid or base. The buffer range is the range of pH values wherein a buffer can effectively resist drastic pH changes. A buffer reaches its maximum effectively in resisting pH changes when the acidic and basic components are equal in concentration. When the acidic and basic components are equal in concentration, the second term on the right side of the Henderson-Hasselbalch equation is equal to 0, making pH equal to pKa. Thus, the buffer's resistance to pH changes is at its maximum when its pH is equal to the pKa. A solution is effective as a buffer when one component is up to 10 times more concentrated than the other component. When the concentration of the acidic component is 10 times that of the basic component, pH equals pKa minus 1. When the concentration of the basic component is 10 times that of the acidic component, pH equals pKa plus 1. Thus, the range of the pH values where a system can act as a buffer is from pKa minus 1 to pKa plus 1. When choosing the most appropriate buffer for a reaction of interest, the desired pH must fall within the buffer range, from pKa minus 1 to pKa plus 1. A reaction is to be observed in a aqueous environment buffered at pH 8.0. Which of the following solutions can be used as a buffer for the reaction? Shown on the table are the buffers ranges for the given buffers. The pH value of 8.0 is within the range of 6.21 to 8.21, which corresponds to the dihydrogen phosphate hydrogen phosphate buffer. Therefore, this buffer is most suitable for the reaction. The Henderson-Hasselbalch equation can be used to calculate for the amounts of acidic and basic components, making up a buffer given the desired pH. Example 4. Calculate the ratio of hydrogen phosphate ion concentration to dihydrogen phosphate ion concentration that can make a solution buffered at pH 7.40. The pKa of dihydrogen phosphate ion is 7.21. Substitute the pH and the pKa to the Henderson-Hasselbalch equation. What is unknown is the base-to-acid concentration ratio. Simplifying gives us the logarithm of the ratio equals 0.21. To solve for the ratio, make both sides of the equation exponent of the base 10. Thus, The ratio equals 10 raised to 0.21, which is equals to 1.6. The ratio of hydrogen phosphate ion concentration to dihydrogen phosphate ion concentration must be 1.6. This means that the buffer must consist of 1.6 mole of hydrogen phosphate ion for every 1 mole of dihydrogen phosphate ion. To summarize, Henderson Hasselbalch equation describes the relationship between the pH of a buffer and the concentrations of buffer's basic and acidic components. Buffer capacity is a measure of a buffer's resistance towards drastic pH changes. Buffer range is a pH range within which a solution can act as a buffer. The effective buffer range is between pKa-1 and pKa plus 1. In choosing most suitable buffer for a system, the working pH must fall within the buffer range. Here are our references. Thank you.
Acid-base equilibria and salt equilibria. Part 9. Henderson-Hasselbalch equation. Quiz. Number 1. Which of the following equations correspond to the Henderson-Hasselbalch equation? A, B, C, or letter D? Number 2. Which of the following expression is equal to acids pKa? A, B, C, or letter D? Number 3. What is the pH of a buffer that consists of 0.0050 molar NH3 and 0.034 molar NH4 positive? pKa is 9.25. A, 9.08, letter B, 9.42, letter C, 8.47, or letter D, 10.01. Number 4. What is the pH of a buffer formed by mixing 10 milliliters 1.0 molar of HCOOH and 90 milliliters of 0.20 molar HCOOK? pKa is equals to 3.75. Letter A, 3.49. Letter B, 3.21. Letter C, 4.01. Or letter D, 2.89. Number 5. What is the pH of a buffer formed by mixing 30 milliliters of 0.40 molar glycine and 20 milliliters of 0.30 molar glycinate? pKa is equals to 9.78. Letter A, 9.99. Letter B, 9.48. Letter C, 10.08. Or letter D, 10.23. Consider the following buffers. Number 6. Which, which of the given buffers has the lowest pH? Letter A, X. Letter B, Y. Letter C, Z. Or letter D, they have equal pH values. Consider the following buffers. Number 7. Which of the given buffers has the greatest buffer capacity? Letter A, X, letter B, Y, letter C, Z, or letter D. They have equal buffer capacities. Consider the following buffers. Number 8. Which of the which of the given buffers can be used to prepare a pH 10 buffer? A, B, C, or letter D? Consider the following buffers. Number 9. Which of the given buffers can be used to prepare a pH of negative 6.8 buffer? Letter A, letter B, letter C, or letter D? Number 10. What must be the ratio of F negative concentration to HF to make a pH of negative 4.00 buffer? pKa is equals to 30.20. Letter A, 0.16. Letter B, 2.4. Letter C, 6.3. Or letter D, 8.1. That's all. Thank you.